Hello, everyone. Hi, I'm Marco from JetBrains, and welcome to my talk, Why You Don't Need to Worry About Scaling Your Java Web Applications. I do have to say I have a bit of a cold, and I hope my voice will hold up throughout the talk, but it's a very interesting topic, so I'll try my best. Now, how did this talk come about? I don't know about you, but I've had that in the past where I've worked on a new project, a new startup, maybe even some sort of a new application. And you build it, and before you launch, a week before you launch, some business person comes in and says, well, what happens if we're going to be the next Amazon tomorrow? Can we scale our application? What happens if tomorrow 10,000 users will use the application? And then, you can mumble something along the lines of, yeah, Kubernetes auto-scaling, and it will kind of work. But I wanted to dig a bit deeper into the whole topic, and I wanted to find out, well, if I have a Java application, where does it spend its CPU, for example? Where does it spend its time, doing I/O requests? Is it maybe memory heavy? Does it consume a ton of memory? And not just, make assumptions about we should maybe just put a number into a box and auto-scale to 10 applications, but really know what is the bottleneck, how would we scale our application, what would make sense, and have cold, hard data and facts, for my decisions. And taking that step one thing further, I don't know if you've ever been on the AWS page where you see the instance types that AWS has. If you're not used to AWS, if you want to boot up a machine in the cloud, you have to specify what specific type of instance you want to boot up with a specific kind of CPU, memory, and so on and so forth, and with a specific price tag. Now, when you look at this page, on the left you have a couple of different sections: general purpose, compute optimized, memory optimized, and a couple more. When you just look at general purpose instances, you can go from M7G, Mac, M6G, M6i, IN, 6A, M5, M5N, until T2. Even just with the general purpose instances, you have a ton of number-letter combinations, specific machines. And I always wanted to know, hey, I have this Java web application. The JVM is quite fast. These are really strong, powerful machines. How would I now know which machine to pick? Could I just save some money by picking the cheapest machine? And that's how the talk started. And my talk is an attempt to give you a framework to find answers to that question, to those questions, to scaling questions, performance questions. So when you go back home to your own project, you can try out the stuff I'm about to show you and come to your own conclusions. Which means the talk is roughly structured in 3 parts. The first part, we're going to do a bit of load testing, because I can't just tell you, yeah, go home with your application and pick the M6G instance. We need to get some data. And by data, you'll see what type of data we're going to collect. We need to collect a lot of profiling data, CPU data, I/O data, whatever have you, and interpret the data in a specific way. I'm going to show you how to do that in the second part of the talk. And at the end, we're going to have some sort of real-life social, political discussions also baked in. Sounds good? Cool. Then I'm going to show you something. The load testing scenario we're going to start with. This is my lovely handwriting. We have a Spring Boot application. The talk is not specific to Spring Boot. It's just that everything that runs on a JVM, I could have taken that. And just for the interested people, Spring Boot application, Spring Boot version 3, it runs a Jetty underneath, not a Tomcat, and it has a JSON endpoint. I'm going to show you that in a second. And as you all probably kind of know from load testing, what every good developer or load tester does is not run the load test on the same machine as the machine being tested, meaning we have a couple of loaders which will generate the load on my Spring Boot application. I'm not just going to have one loader, because I noticed it's actually relatively easy to overload a loader when you crank up the load. So I just want to make sure I have, in this case, 4 specific loaders which will generate the load. And then there's something else, a tiny concept which is debatable. but I learned this from the chatty maintainers, actually, who helped me out a lot with this talk at the beginning, is the loaders are only there to crank up the load against my server. And the probe actually simulates a single user. And the probe just, executes 1-2 requests per second against the server. And the loaders do not record their latency, so how long did the request take. It's all done just by the probe. The probe, finds out, hey, suddenly my requests take 5 seconds or 2 seconds, whenever the load increased. That is the scenario I have prepared. It runs in AWS in the cloud. I have a couple of machines set up. And I also have a code repository where you can later on check out everything I'm doing and do the stuff yourself. Which means it's code time. I'm going to first show you what the Spring Boot application looks like, because it is so dead simple. If you're not used to Spring Boot, don't worry. It's just a couple lines of code. There's one REST controller, which means there's going to be one JSON endpoint. We're going to make it very simple at the beginning, meaning I don't want to immediately start out with my microservice landscape with 20 different instances whatsoever, and a database and a message queue involved. I wanted to show you everything, the concepts, with the smallest, tiniest example, and you can take these concepts later on and apply them to the bigger picture. Simple means we have one text controller, one endpoint. The endpoint returns a text array object, meaning that will be translated to JSON. And it has 2 fields. It will always say, hey, we have the German VAT. And it's always going to be a random number. Every time you hit the endpoint, you get a random number for the VAT. And it's just because I wanted to simulate some work being done here. But that's all there is to it. And then I have, as mentioned, my load testing project. And actually, it mainly consists of one class, and I'm just going to run it now because it's going to take a while. I'm doing this live. And while it's running, let me show you, it's a tiny bit of code, scrolling up and down here. I'm not using a specific framework like JMeter or Gatling, a specific tool, because again, the chatty maintainers have written a tiny Java framework, performance framework, that allows you to orchestrate and run these load tests and generate all the data you're about to see in a second. In any case, the load testing scenario you saw early on, we're going to run it 4 times. 4 times means the first run, every one of my loaders generates 250 requests per second, already a relatively high number, against my server, which means in total, because it's 4 loaders, we're going to start with 1,000 requests per second. And then a second run with 5,000 requests per second, a third run with 7,500, and then just because we can, 20,000 requests per second. And just at this point, think about what do you think, what's going to happen? Is that going to be an issue for my server? I picked an M5 machine, which has 4 CPUs, I think 16 gigabytes of memory. Do you think the server will easily handle 20,000 requests, 100,000 requests? No optimization, no nothing. Yeah, just think about it, and I'll show you some data in a second. Which means, while the load test is running and the scenario is running, I'm going to go back to my drawing board, and you can enjoy a bit of my handwriting. Which means, load testing is fine so far. I have been babbling about we need to collect some data. What type of data do we need to collect? There's number one, what I would call the big picture data. Big picture. And by big picture, I mean we need snapshots of the CPU usage. We want to find out during the load test, hey, my server, what was the CPU usage like? I want to get data on memory usage. Just in general, are we using a gigabyte of memory, 2 gigabytes, 5? What happens here? I want to get data on maybe even my network adapter. For example, is maybe the network bandwidth a problem? In this case, it's not going to be the problem because we're just going to send a bit of JSON, back and forth. But it's good to have that data. I want to get I/O data. If I'm reading in lots of files, for example, how do my hard drives behave? That's the big picture. And then we also need something else. We need what I would call the drill down. Drill down means it's nice to see the CPU snapshot of the whole machine, of the whole operating system, but where specifically was the time spent inside my application, CPU-wise, for example, or memory-wise, or I/O-wise. And that means we have to do some profiling, and we're going to spend a lot of time, actually, in a second, on profiling data. With the async profiler, look at flame graphs. Just a quick question, who has worked with flame graphs before, or, really? Okay, a couple of people, cool. You might also want to get what I would call business logic latencies. For example, and you can tell I'm not writing so often with my hands. For example, you might check out how many SQL statements are you executing, how long do these SQL statements take, HTTP client tracking how long do my requests take to another system, just in general measuring the latencies in your application server, where is time being spent. We're not going to spend as much time or little time on that actually, because it's a whole other topic. But as a general overview, important. Profiling, business logic latencies, also a nice topic. You want to get garbage collection logs, for example. We can spend tons of time on garbage collection here, and pauses your JVM does. There's a tool called jhiccup, for example, which allows you to find out why did my JVM just stall and why were there problems. But it doesn't matter. At the end of the day, when you run this load test, you have to not just run the load test, send 1,000 requests and then just look at the latencies you get. You need to collect the data, big picture data, the drill down data, and then be able to interpret that data. And that's what we're going to do now. Because this magic class I've shown you before, what it does is it tries to get that data. So it tries to get the big picture data, drill down data, with simple Linux tools. You might be wondering, hey, you could have made the talk kind of vendor-specific. For example, in AWS, you have nice dashboards where you see CPU usage, other stuff. I wanted to use simple Linux tools without being vendor-specific, and I'm just going to show you what that data looks like now, hopefully with the first test run having finished. Let's see what my debug log says. Yes, that looks actually good. OK, cool. So the first test run has finished 1,000 requests per second. Now what I did is, this script, as mentioned, it runs, for example, the profiler on the server, generates the data during the load test, and at the end, downloads the data locally into a folder, into my project, into a so-called results folder. You'll see multiple folders pop up here. One folder for every test run. We have 4 test runs, so at the end of the day, we're going to have 4 folders, including an additional plot folder, which is what I would like to start with. When you look at the plot, what do we see here? Oh, right, the second test run also has finished already. OK, so I'll show you what you see here. First off, you see an HDR histogram here, and I've had discussions with people before if that is indeed a histogram. It is a high dynamic range histogram, and you can read about that online, what it looks like. Just to explain you what you see here, in case you've never seen such a histogram before. This is the latencies, the probe, remember, the single user machine, which does 1-2 requests per second during the load test. The latencies the probe got when sending the requests. On the y-axis, you see the latency in microseconds, unfortunately. If you want to convert it to milliseconds, divided by 1,000. So when the probe did the requests, they took between 1 millisecond and 1.4 milliseconds, which is nothing, because all these, the probe lives in the same AWS network, so in the same zone as my server. The server hasn't got to do much work, so it's just in the millisecond range, right? On the, you see two lines here. The blue line is for my 1,000 requests per second run, and the red line here is for my 5,000 requests per second test run. And these two lines, you see the latencies on the y-axis. On the x-axis, you see the percentile, meaning when you go along the lines, you can say here for the red line that 50% of the requests during my 5,000 RPS run, they took up or less than 1,075 microseconds, so 1 millisecond. And then you can go up here and see the 90th percentile, say 90% of the requests, they took less than 1,170 microseconds, like that. It just gives you a quick overview of when we crank up the load. Later on, we'll see more lines here, 4 lines hopefully. How did the latencies change? Are we going to run into scaling issues potentially? And at the moment, it's just two lines basically on top of each other in the millisecond range. That is just a quick check, initial check, what I found helpful to do when you run these type of load tests. All right, back here. Let me show you the data we collected. I have this folder for my first test run, also for the second test run later on, with a couple of subfolders. So for my loaders, I have 4 loaders, including their IP addresses, so I have 4 subfolders. I have data for my probe, I have data for my server. And we're going to go through that data roughly now. Starting with my first loader. I told you about operating system data, meaning I have a CPU log, a memory log, a network log. Again, it might look very different depending on the cloud provider you're using, but this is just simple Linux tools. How you might want to read this CPU snapshot. Simple, my load test runs for 30 seconds, and I just take CPU snapshots every 10 seconds. So what you actually see is 1, 2, 3 different CPU snapshots in here. And you can see that, yes, well, we have 4 CPUs, but we can ignore all of that and just have a look at the average line, so the all line here, all the CPUs combined. And again, ignore all the columns and just focus on the very rightmost, on the outer rightmost column. It's the idle column. What it says is that during the load test, my loader CPU was idle for 96% of the time, 99% of the time, 99% of the time. So my loader didn't have to do much work to produce the load, CPU-wise. Especially when you crank up the load later on and you think that your loader has to send out 10,000 of requests, you will find that number go down considerably, and then you'll know you need more loaders, for example. Right. We do the same thing with simple Linux tools for memory, for example. You can just get the big picture overview where you say, hey, I have 15 gigabytes of memory. This is 4 snapshots here, actually, not just 3. And the loader is just using 400 megabytes of memory. It's a fair amount of memory, but that's fine. We still have plenty of room left. The same for my network adapter, actually. Don't be scared. I'll tell you what to ignore here, because now we have 2 rows making 1 snapshot. So this is 1 snapshot of my network adapter, another snapshot of my adapter, and a 3rd snapshot. And you only want to have a look at the received kilobytes and transmitted kilobytes a second columns, where you will find out how much data did you get, how much data did you send out. I personally haven't been part of a project where my network adapter has been the bottleneck in scaling, right? But I've tried to make it work, to come up with the example for this talk where my network adapter is actually the problem. The funny thing is, just for the interested people, if you want to do that in real life, AWS actually counts the number of TCP/IP packages it receives per instance. And before you hit the bandwidth limit, you actually hit the limit of packages received, and then AWS will start dropping your packages, and you will get faulty responses, and you'll be stuck in a rabbit hole figuring out what is going on. Just, if anyone wants to go down that path. Right. So, you saw that big picture data. Just gives you a big overview of what just happened. In terms of just a tiny caveat, because it also happened to me before, when you do load tests, also make sure, obviously, that when you run it, that all your responses, for example, in the case of HTTP, they come back with an HTTP 200. So you're not, celebrating because everything is so fast, and that only happened because, you had validation errors and stuff like that, and most of your business logic wasn't executed at all. It's just a tiny reminder. And this text file is just a representation for my specific use case, where I can see that at the second 0 of my load test, I sent out 250 requests exactly, and they all came back with 200, right? And then I can just have a visual check and find out, hey, my load test seems to be, working as expected. Or if you want to, by the way, you can also turn that into what I did, a visual representation. Please ignore the upper part here. Just some sort of a throughput line where whenever you see these straight throughput lines, you can be happy because everything worked roughly as expected. You wanted to send 1,000 requests per send. The moment you're getting big weird lines, the moment you have a problem here. All right, so we have that sort of data, and it's the same for every other loader. I don't have to get into details here. It gets interesting with the server. I said we're not going to focus so much on garbage collection and on SQL statements because we're not executing any SQL statements. I want to spend a fair amount of time on profiling data. And if you've ever run an async profiler on a JVM project before, you might know that essentially you can make 3 profiles. You can profile your CPU, so where's your CPU time being spent? You can profile your memory, where is most memory being spent in your code specifically? And something which is called wall time, meaning where do your threads spend most of their time, maybe waiting for HTTP requests and whatnot. What I choose to do is have a CPU profile made for every test run. And I'm just going to quickly open it up and show it to you. If you've never seen it before, it might just look like a fair amount of fancy colors. Don't worry about it. I'll walk you through it one by one. You can ignore everything you're seeing now. For now, I'll just literally want to take you through it one by one. What you see here is only CPU being spent in your application. Where was my CPU being spent? The big colors mean different things. The green color means CPU spent in your application code, which means your Java code, Spring, Boot, Jetty, my text controller servlet, whatsoever. That's the green bars. The yellow bars is times CPU spent in the C++ code of the JVM. And in this case, it's actually the JIT compiler. You can even see here the C2 compiler. It's a just-in-time compiler, which tries to optimize the code. And actually, that is a problem for this very flame graph, because I don't do much of a warm-up during this load test now as part of this presentation, which actually means a fair amount of work is being spent in the just-in-time compilation. Red means CPU being spent in operating system calls. So my Java code says, hey, operating system, please start a thread for me, for example, or please read some bytes from the disk. And orange is CPU being spent inside the kernel. It's something that we rarely, as Java developers, worry about. So where does the kernel, the Linux kernel, spend its CPU time on? But you can actually also see it here inside a flame graph. The rest is just basically what you see is a stack trace. And the bar here at the very bottom, the all bar, hopefully you can see that, says, well, this is 100% of the CPU time being spent for this very load test. When I go up here on the left side, on my green side, I see it all starts with a thread.run method. I hope you can read that at the back. If not, roughly 51.54% of the CPU time are being spent in thread.run. And that is because essentially everything that your web server does, at some point runs inside a thread. when you go up, you can see that you have the Jetty packages coming up, Jetty, a fair amount of Jetty work. At some point, the packages turn into Spring. That's when Spring Boot takes over, right? And your code ends up in the Spring Boot universe. And then hopefully at some point, somewhere, my little tiny text controller should show up. Actually, instead of just searching for it, clicking through it, you can just search. I don't know if anyone saw that something just happened here in the flame graph. A tiny, tiny piece of code got purple, and that is where my text controller is. And I'll show you, actually, let me zoom in, because you can also, let's say I want to ignore the rest here, the right side, the just-in-time compilation. So I'll just zoom in on the flame graph and start roughly here, where my Spring Dispatcher servlet, starts, right? The purple thingy, this here, is my text controller, the text rate method. And actually, my flame graph tells me that CPU-wise, 0.13% of the time was spent inside my text controller, which is obviously nothing, and it's a bit of a synthetic example, but it gives you a great idea of, hey, my text controller, how much CPU does it burn? Or how much memory would it burn? Or whatever, what would it burn? And when you go to the left side, what you can actually see is, if you look at the sizes of the bars, you could say, hey, where's the most amount of CPU time going to? And then you can find out that, well, it looks like just visually that Jackson, whatever converts my object to JSON later on, seems to have a pretty big chunk of CPU time, or let's say 6% of the time. So 6% of the CPU time is being spent in Jackson, which is not a whole lot, and obviously which does most of the work, converting my object to JSON. But that's essentially it for this very specific example. All right, now that you kind of know how to read flame graphs, we're going to do a bit more realistic example. Because what I did is, I thought, hey, let's take Spring Pack Clinic, for example. Maybe most of you have seen Spring Pack Clinic before. It's a Spring Boot demo application. And I ran my load test, including collecting all the data against Spring Pack Clinic. More specifically, against one endpoint only, the vet endpoint, which gives me back a list of 6 or 7 veterinarians. It's such a hard word for me to say. A list of 7 vets. And I wanted to find out, hey, by just hitting the endpoint, where does Pet Clinic actually waste most of its memory, CPU, whatever have you, right? And I'd like to show you the data. So I did that. Again, I have the data inside a folder, results Spring Pet Clinic folder. Let me just open up the plot. I did one test run, and I said, for whatever reason, hey, Spring Pack Clinic, I want to send 2,300 requests a second towards that vet endpoint. Interestingly enough, what you can see here with the latencies I got, these latencies are seconds, right? So that means 2 seconds, 4 seconds, 6 seconds, 8 seconds. So just by hitting this one tiny endpoint with 2,000 requests per second, roughly, you already get latencies in the seconds range, which is quite weird. I thought, okay, that is definitely less than what I've seen with my tiny JSON endpoint. But again, I didn't know why is that the case? Was it CPU, memory, or what was it? Limiting the scale here. Meaning, let's go back and dig down a bit deeper into the server data. Server OS data, the CPU log. And when you look at the CPU log here, remember you only need to look at the right side of this output, the idle column. You can see that the CPU was pretty much dead throughout the load test. So just 0% idle, 0% idle, 0% idle. The CPU was hammered. And I wanted to find out, hey, why was the CPU hammered? What happened? Where did the CPU go? Again, I want you to think about that. What you might think now, where did the CPU go in that tiny example? Before I open up the magic flame graph, which gives you that information. So, the flame graph for my pet clinic application. Very similar to what you've seen before. On the left side, the application code, the green code. Right side, just-in-time compilation. We can ignore that for now. Again, I'm going to drill a bit deeper. I'm going to start, at the point where the dispatcher servlet, Spring's dispatcher servlet, takes my request and forwards it to my controller. And then I'm going to do a tiny search. I think it's called vet controller. Let's see. Or was it called vets controller? It's actually tricky to see because, again, I'll have to double check. It is such a small percentage of the time, again, like 0% of the time, being actually spent in fetching the data that goes into my HTML template. The interesting thing is, however, when you look at it and look at this tiny bar here or this big bar here, you can see that 56% of the time were spent in Thymeleaf template engine.process, meaning most of the CPU time during the whole load test went directly into Thymeleaf, going through the template, handling the tags, and filling in the data, not catching the data and computing the data beforehand, but actually the whole load test is some sort of a CPU benchmark for Thymeleaf. And if we increase CPUs, yes, we can, increase the request per second we have here, but Thymeleaf is relatively CPU heavy, a bit slow. And this is not a diss on Thymeleaf. I'm using it myself and have used it myself in many projects. But it's just something to be, roughly aware of, that every framework, every library, whatever, could have a specific implication on CPU memory I/O. Okay, so we have that, the Thymeleaf example. Let's go back and see, by the way, with my tiny example from before. Remember, we wanted to do 4 load test runs. And they all have finished by now, I think. Yes. And I can have a look at the plot. Plot looks a bit different now. So there's more lines, and actually what you see here at the bottom is there's 3 lines on top of each other, which is why you can't differentiate them anymore. But there's the 1,000 RPS line, the 5,000 RPS line, and the 7,500 RPS line here on top of each other. They just took milliseconds again, between 1 and 2 milliseconds, the requests. And then the last test run was kind of a Hail Mary, 20,000 requests per second, and then suddenly the response times go up crazy. So for example, 50% of the requests now take up until 52 milliseconds, and then 100 milliseconds, 200 milliseconds, 500 milliseconds. So in fact, 100 times more, 200 times more, 300 times more. Which means the truth is, somewhere between 7,500 and 20,000 requests per second, this very specific machine has issues handling the requests. It still, serves the requests one after another, but they just take more time. And I would have to run, more load tests to find out the sweet spot. Right. Again, let's quickly double check this with the 20,000 requests per second. Let's drill down a bit on the CPU data in the last test run. So I'm just going to open the folder. I'm going to go to server, OS, open up the CPU log. I'm going to go to the right. And I can see that, at least for 20 seconds, again, my CPU in that case was pretty much dead, right? Again, I would have to scale my CPU if I wanted to have more requests in that very specific example. But it's just, what I wanted to take away is that when you do the load tests, and this is very CPU-heavy talk because it's so easy to demonstrate. And in real life, you probably have more I/O-specific workflows where you send off many requests to other systems. But the same, concepts, the same applies. You want to collect the data. You want to make sure for every test run, for every participant, of your load test, where does the time go, CPU, memory, I/O-wise, and then draw your conclusions. Okay, now. Enough data for now. What I want to do is closing remarks or a couple of real-world challenges when you do all this. Obviously, practical challenges and hints. You've just seen me use a very synthetic example, meaning we had this one application server and we just hit one endpoint. And unless you have an application like that, a web shop where people just hit the password reset endpoint for whatever reason endlessly, then this is a very, very simple example. And obviously you need to reproduce this, what you just saw, with real-world usage scenarios, so people, flowing through your web shop, for example, or if it's an API, having relatively realistic API usage scenarios against a prod-like environment. And that is easier said than done. It's a whole other topic, because even with containerized deployments and whatnot, you'll find that the amount of data or density of the data in your database will also influence, latencies and whatnot, and it's not super simple to regenerate, a prod-like environment. It's something to keep in mind, something where we could have plenty of talks on about, but that is definitely a challenge in the real world. However, what I found is, as some sort of a first instinct, I always wanted, especially microservice deployments, where you have, a huge landscape of, different microservices. What is the weakest link? Meaning, which part of my chain breaks down first? It doesn't help if, for example, the database is the weakest link, and I increase the load by adding more and more and more application servers up front. They will just hammer the database more and more and more, and that will actually, the way of auto-scaling makes things worse. You need to find out where is the actual issue, and not just think of, let's just randomly add 20 machines and then everything will be solved automatically. Find the weakest link. And what helps you with that, by the way, is use distributed flame graphs. It's pretty cool. What you can do is you can collect these flame graphs you saw earlier across multiple machines, and then condense them into one big flame graph. And then you'll actually find out CPU, memory, I/O-wise, where time was spent across your whole microservice landscape. You'll need to Google for it, but it's just something to keep in mind. The next topic. And this is kind of almost my favorite topic. It's expectation management. So when someone comes to you and says, hey, we're going to be the next Amazon tomorrow, the likelihood is very high, almost 100%, that you're not going to be the next Amazon tomorrow. And business people obviously always like to say, hey, 10,000 users, 100,000 users. The funny thing is, unless you happen to be one of, let's say the Chinese ones, Alipay, whatever, or Facebook or Google, you're not going to run into these, scaling problems, having to serve 100,000 users, just from the get-go tomorrow. It doesn't happen overnight. It also didn't happen for Amazon overnight to become Amazon scale. So the business has to follow suit, obviously. That obviously is just me claiming it. It's like, Marco, why? I'm really going to be the next Amazon tomorrow. Again, I wanted to show you some data. One of the few companies who publishes performance data is the Stack Exchange network, which is the network behind Stack Overflow and all the other stacks, so to speak. And they have this performance page. And when you scroll down, you can see they have, in addition to the SQL servers and Redis and whatever, they have 9 web servers, and on average, they serve 300 requests per second, consistently, which is a fair amount. 300, 300, 300. At peak time, like 450 requests per second. And I'm not claiming that my servlet I wrote earlier is going to handle the load here without a problem, but I wanted to give you an idea of the orders of magnitude you're talking about. Hundreds of requests per second consistently throughout the day is a fair amount of load. Stack Overflow or Stack Exchange is among the top 100 most popular websites online. And most business internal applications, for example, are happy to get tens of requests consistently throughout the day. Yeah? So what you saw me do earlier, where we said, hey, now let's worry about 1,000 requests per second, 10,000 requests per second, 20,000 requests per second. It kind of fulfilled the urge, which we all have. We want to see a machine break down, and we want to have a number where we say, but this can only handle 30,000 requests per second. But the funny thing is, it all doesn't matter. That is just, just number vanity metrics. What you'll need to find out is, what is my expected load I have throughout the day, which is very likely going to be much less. Not worry so much about the 10,000 requests per second, unless, again, you're working for Alipay, but then you probably wouldn't be listening to me on scaling so far. They have crazy numbers, Alipay. I looked them up, where you have every new year, after every new year, in the first 24 hours, I don't know, 100,000 of transactions. It's literally crazy. Right, so it's just keeping yourself in check here. And that means not just keeping, let's say, you in check personally as a developer, because we always want to work on the fancy things and the shiny things and really see, hey, how much does it scale? But also telling your business person, hey, where do these numbers come from? Why do you think we get 10,000 people tomorrow? Did we have like 5,000 people yesterday, and they all said they're going to bring their friends to our website, for example, and now we really need to 10,000? It's like a line. It doesn't happen overnight. And just to finish this off with e-commerce. So my colleague, Marit at JetBrains, she also worked at one of the big retailers in the Netherlands, and they had pretty high traffic throughout the year with e-commerce, just people browsing the shop, buying stuff. And she said that Black Friday is also not a problem, because Black Friday is going to happen, and then you can scale up in advance. You know from the past what were the issues, how many servers do I need, what parts of my landscape broke down, where do we need to make stuff better. That is also not an issue, because it's expected. What Marit says, for her, what was completely unexpected, and for the whole company, was the launch of the PS5. Because it was announced, and then people literally hammered the website trying to reserve a PS5. They wrote scripts, trying to block and reserve a PS5. And that is some sort of the unexpected load you'll get, which I guess they were unprepared for. And she has to, write a post about how they, fixed it, how they fixed it after all. Right. And last but not least, performance awareness. So, as mentioned before, performance is often kind of, treated as an afterthought. We always worry about architecture, blah, blah, and all sorts of stuff. And then at the end of the day, you say, okay, performance now, what does it look like? I'm not saying you need to, print out the assembler statements your JVM, generates when it runs your code and dig that deep. But it definitely helps if during development, at least, from time to time, you spend some time on your flame graph and you get some sort of an understanding of how does my application actually perform and where do my resources go to. You often can't, especially, imagine you had a legacy project with Thymeleaf and for whatever reason you thought, now I need to switch it out with FreeMarker, for example. I did that for testing, and FreeMarker is a lot more CPU efficient. It also does a lot less work. Though. You're not going to do that in a real-life project. But for your next project, you might just be aware of certain specific performance factors involved in your project. You might choose certain libraries or frameworks or whatever, depending on that. I'm just saying your next project will benefit, and that keeping performance in mind is a good thing, and not just hoping that the ops person or the DevOps person at the end of the day will just put it on any machine and then it will just magically run and that's it. Further reading, I mentioned the source code that I executed earlier. There's a repository. There's also a repository for the Chatty Performance project. There is the third link here. By the way, you don't have to take a picture just now. You'll see a QR code on the next slide. With the link to the slides and everything. I just wanted to highlight that the third one here is Christoph. I'm not saying his name right. He wrote an insane manual on profiling Java applications. I can only recommend it. It's really good stuff. And then obviously, I also blog and YouTube about it. But just some sort of a couple of closing words. If you have this framework in mind, when you do your load tests, you regularly do your load tests. Collect the data, big picture data, drill down data, and then interpret the data and find out, where is the time being spent. If you do a bit of reading up on the topic, and a bit of expectation management, so a bit of, let's call it a social challenge inside your company. Then hopefully you truly don't need to worry about scaling your Java web apps anymore. Thank you.